Dear friends, now I will start the part 3 of our time capsule project. In the part 3, I'll talk about mitigation of landslides by drainage measures. In that, I will take case histories from Southern Expressway construction, Waterwiller and Padulugattunma landslides. When you go back to this famous statement by Carl Tersagi, if a slope has started to move, the means of stopping the movement must be adapted to the process which started the slide. So earlier we talked about the investigations, various monitoring aspects and so forth. So with all these activities, we have to identify the reason for the slow movement, where the failure surfaces, at what kind of rainfall intensities the movements will initiate. So once we have done the necessary studies and identified the reasons for slow movement, then we have to attack the cause of movement and do the necessary engineering interventions to rectify the slope, to enhance the stability of the slope. So what are the basic remedial measures, especially with rain-induced landslides? We can categorize that into these four: modification of the slope geometry, drainage, retaining structures, and internal slope reinforcements. So with rain-induced landslides, the primary task or primary activity in enhance the stability is by drainage. Along with that, there would be certain modifications in the slope geometry. So in this part, we will be talking basically about the drainage measures. Talking about the modification of slope geometry, in that we may remove material from the area driving the landslide, the upper part of the landslide, and add material to the toe of the landslide, or reduce the general slope angle. So along with the general drainage measures, these geometry changes would also be necessary in the rectification of rain-induced landslides, so reducing the risk of rain-induced landslide. Just one case of this geometric change. So in this potentially vulnerable site, so this weight is removed from the upper area. Weight is removed from the upper area, and weight is placed on the lower area of the slide. So this is something that we can do to one step that we can do to prevent initiation of movements along that. So I will elaborate these things further along with the drainage measures. Now, in the part 1 in the analysis, I have shown how the infiltration causes loss of matrix action and development of poor water pressures. So there, I also showed how the factor of safety deteriorates with the continued infiltration, continued rainfall. So we can't prevent rainfall, so we have to find out what to do to minimize infiltration, reduce infiltration, minimize the loss of matrix action, and reduce the pore pressure building up. So this can be achieved to a certain extent by improving the surface drainage. Sometimes that may not be adequate. We have to improve the subsurface drainage as well. The surface drainage can be enhanced by construction of cut-off drains, berm drains, etc. That is, we regulate the flow of water on the surface. We can collect the water and try to and facilitate the rapid movement of water out of the critical site. So in that case, we use surface drain, cut-off drains, berm drains. Shallow or deep trench drains will also be helpful. Now we can make use of vegetation. So vegetation will deflect the water falling on the surface. So it will minimize erosion and reduce infiltration. So when we cannot get vegetation in, like in highly fractured rock, some artificial slope cover such as shotcrete will be necessary. I talked about relic joints, the joints in the bedrock, and they being present as relic joints in the residual soils. So they are a source of weakness. Water can infiltrate into that. So if there are exposed relic joints, we need to seal them and have special protection on them. Then that is all surface drainage measures. So, so we cannot prevent the infiltration 100% by surface drainage measures. Anyway, there will be some amount of water moving into the slope. So we can have vertical wells with gravity drain or pumping wells to extract already infiltrated water, or we can have subsurface drains which are working under gravity principle to get the water out of the soil. So there are different measures that we can take. These measures are site specific. So we'll have to adopt the most appropriate measure depending on the site condition. These are some surface drainage measures adopted in the construction of the Southern Expressway. The natural sloping ground, which was like that, was cut to a steeper slope to make way for this highway. So there was a lot of water coming from a further upslope. So this cut-off drain was constructed at the top of the cut so that water is not coming, the great amount of water was intercepted and taken away through that, right? Water this area cut slope was even subjected to the water directly falling on that. So these cuts were done with several berms. So this is you can see here there was a drain here directing water, collecting water from the top and bringing here, and it had been connected to a cascade drain over here, and there is a berm drain collecting the water over this region. So without allowing the water to flow throughout, we have berm drains at intermediate levels to collect water, right? So this is again a similar thing, a berm drain. You see this deeper, so that having calculated, having estimated the kind of amount of flow that can be expected, we have to have a drain of adequate capacity. And this is going to be connected to a cascade drain, which will go down here. And one important thing with these surface drainage structures is that they should be constructed in situ. You can't get precast units and place on the cut slope and so assume it to work perfectly. So with the precast units, there is no proper connection between the existing ground and the drainage element. So there can be leakage through that. So in all these cases, for that to be effective, this should be constructed in situ. So then that binds with the existing soil profile without leaving any gaps or any room for leakage. You can see here the cut of the berm drain here, and it is sloped into this cascade drain, and water is coming through that. So that cover is provided here to prevent water splashing into the road surface. This is another location where drainage was given a lot of attention. So there's further high slope up there. There was a lot of water coming through that. So they have it in 3 berms, right? So there is that water directed through that, through this cascade drain, to the berm drain, and further cascade drains are there. And so this halfway through the implementation of the drainage solution, and if the drainage solution is not complete, so during a heavy rainfall that occurred at that stage, you can see how much of water is flowing in an uncontrolled manner. So if these surface drains were not properly installed, there will be that kind of flow all over the surface. If you remember, I showed you a picture here, a picture earlier, where this kind of uncontrolled flow of water created a landslide after a few years. So this is before implementing the full drainage measures. Some parts of the berm drains and the cascade drains were not done by that time. Now, the same section, after implementing all proposed drainage measures, you can see these cascade drains bring the water down, and then water coming along this berm drain and getting out to the road drains here. So we have to have cascade drains at appropriate intervals, having assessed the quantity of flow. Right? Sometimes you might not be able to do a cutting to get a cut-off drain, right? So this is sloping ground here, where excavation is done for a ground reservoir. So at the edge of the road, so this area, there were boulders, there were boudinate structures in a matrix of soil. So trying to cut to make a drain here would have caused some further instability. So therefore, the road surface, which was concrete, right, and L drain was connected to that. So that is the L drain, right? Sloping ground was over here. So L drain was connected. There was the side drain of the road on the other side. So there is no water flowing into the steep slope, right? The steep slope. So that is the condition. There's some soil thickness above the rock. So that is vulnerable. So water was not allowed to move into the sloping ground. It is intercepted here by the cascade drain. So we have to think of the site-specific situations and come up with most appropriate surface drainage solution. Along with the surface drainage, surface erosion protection measures are to be taken. Now, in this particular site, you can see there are berm drains like that, and then the berm drains are sloped into the cascade drain. So there are cascade drains bringing it down. Now, this is an area where the exposed material is soil, residual soil. So in that, vegetation had been introduced. I showed you the highly heterogeneous nature in our slope profiles, and over here it was closely fractured rock, weathered and with closely spaced structures. So it was not possible to introduce vegetation into that, and these small particles were getting disintegrated and moving down. So it has to be protected. So shotcreting was done there to protect those the unstable pieces of rock in this highly jointed rock mass. Talking about vegetation, how do we introduce vegetation? The advantages of vegetation. Vegetation will clearly prevent the surface erosion, and it enhances the cohesion at shallow levels up to maybe even a meter by closely binding with the closely binding root system. There are many studies done with enhanced cohesion at shallow levels. Deeper roots will provide a reinforcing action, as in the case of soil nailing. When the rainfall falls on the sloping ground, foliage intercept rainfall without letting everything fall onto the ground. So it causes absorptive losses there, and subsequently, when the water gets into the ground, it causes it extracts moisture from that, cause transpiration process, evapotranspiration for the life, for the living of the particular tree, right? So there are different ways that the vegetation helps to enhance the stability of a slope. So based on the level of weathering and the nature of the soil exposed, different techniques can be adopted to introduce the vegetation. If it is highly weathered, the vegetation, surface vegetation can be introduced by turfing, or it is much less weathered, but still a residual soil, you can use the hydroseeding technique. So this is the hydrotation technique. Where you spray the mixture of topsoil, seeds, and fertilizer into the slope surface. Now, till the seeds germinate and the roots are grown, you have to protect it from getting eroded by rainfall. So we use a coir mat. In this case, we have used a coir mat to provide that protection till the roots are grown and till the seeds are germinated. Right. So this is the situation of turfing. Right. These sods were placed on the ground, and till they get interacted with the ground, till the roots grow up. So they were there was this the timpis, right? You nail that into the ground with a piece of timber. So this is hydroseeding used to as a surface protection device with this wire mesh there. And this shows the hydroseeding done with a straw mat, right? So the hydroseeding had been done and the surface had been covered by this straw mat, and they are doing controlled watering till the seeds germinate. So you can see a later stage where now the vegetation is growing up, showing up. Right. So those are surface drainage measures. In certain situations with low groundwater table, right, we may be able to enhance the stability to an adequate level with surface drainage only, but not always. In many sites, we have to install subsurface drainage in addition to the surface drainage measures. So subsurface drainage facilitate the movement of water that is already gone into the soil and accelerate the pore pressure dissipation. We can use the subsurface drainage to lower the groundwater table. So these are different measures, combination of surface and subsurface drainage. So there's a cutoff drain here and a trench drain here, a deeper trench filled with permeable material covered with a geotextile. So water from further lower levels can come into an escape, and a lowering of the groundwater table can be expected due to this. And this cutoff drain will prevent the lot of water from the upper levels of the slope moving into the critical slope area. So that is the surface drain, right? So here you can see that the soil rock interface. So that is the more vulnerable surface, right? With a lot of water getting in here, pore pressure will build up there, and a failure can take place at the boundary as illustrated there, right? So it's a combination of surface and surface drainage measures with a trench drain. Then coming back to the Waterwala landslide, which I showed you before. So this slide had been there from early 1950s and finally rectified in 1990. So I will show you the sliding mass, the failure surface in the next slide. So it is getting activated during the periods of heavy rain. In this particular night, there had been movement along the failure surface and railway track has subsided. So as a result, the night train went down the slope. So this is the plan area of the landslide. So that is the railway track. Identified boundary of the landslide is here. It is affecting about 150-meter length in the railway track. Thorough investigations were done for this landslide, so about 10-15 years, finally rectified in mid-1990s, about 93, 94. So through these investigations, we identified the failure surface, which is at a depth of about 30 to 35 meters in the colluvial residual soil boundary. Now, a lot of movements have taken place on this surface over about 30-40 years, and the soil here has come to the residual stress state, right? Say in initial site, right? So it will, if you take the stress strain curve, in the initial site, the state of stress, state of strain, deformation will be closer to the peak. But if a lot of movements take place over this surface over years, right, state will be more close to residual. So when we were doing the analysis, we found that the shear strengths here have come down to residual values. Otherwise, failure cannot happen. Failure is happening due to the rise of groundwater table from here to here during the rainy season. So that is the groundwater table during the dry season. With the rainy season, it rises up, and that was the railway track. So as a result, during the periods of heavy weather, there is some movements happening along the failure surface, which is at the residual state. So then how to rectify this? It is not a very steep slope, right? So rectification should be based on the reason for failure. You have to attack the reason for failure. So rectification has to be through drainage measures, surface drainage as well as subsurface drainage. So this illustrates the measures adopted. There were cut-off drains done at different levels to divert the water coming into this critical slope area, right? So that is surface drainage. And there were educted pumping wells drilled in here to pump the water out and lower the groundwater table. But it is done at the initial stages, but it is not an appropriate long-term measure because pumping water from larger number of wells for a longer period will incur a lot of cost, and cost will be quite high. So therefore, in this case, they proposed directional drains. A drain initiated from here, going just below the critical identified failure surface and daylighting somewhere there. So there were 13 such drains done to cover up the planned area, and high density polyethylene HDPE pipes which were perforated were installed in those drains. So the critical area, target area, is this failure surface. The movements are happening along this failure surface. You have to provide rapid dissipation of pore pressure, prevent the rise of water table from here to here, prevent rapid dissipation of pore pressure closer to this identified shear surface. So that's why through the direction drilling technique, they did a computer controlled drainage solution following this path. Under that, 13 HDPE drains were installed. So with that, as the water table attempt to rise during the periods of heavy rain, so the water has a clear escape route through that. So this shows that measure the directional drains, surface drains, and piping wells. Piping wells were installed at the early stages. So these are some pictures of this surface drains, a picture taken by me around 1993, 94. So these were the pumping wells, eductors connected to this horizontal tube. So they were operated to lower the groundwater table at the initial stages of the rectification. And this shows the plan view. So that is the plan view of the sliding area. So to cover up the plan view, there were 13 drains like that, right? Installed from the lower level, covering up this plan area. So this is a typical sample of a HDPE pipe, which has high resistance to deformation. It was told that they can experience a strain up to 800% before any rupture. So when you install a drainage device, subsurface drainage device in a landslide site, you'll have to be very careful about its flexibility. If it breaks easily with some little movement, then the whole purpose is lost. So you have to install something which has very high resistance to fracture, right? So in this exercise, they did the boring along the just under the failure surface. So they used the technique called directional drilling technique, which had been used in the oil industry to install oil pipes below water streams. So it was the first time that water parts. This was the first time that this particular technique had been used in the stabilization of a landslide. The picture I have taken in 1995 showing the outlets, right? The railway track is further up. These are the outlets of these 13 drains. So now the water is flowing under gravity. There is no pumping required. Water is flowing under gravity. This is a picture that I took in 2012. The same site, you can see still they are working, right? There is drainage through that. There is some blockage of the drains, we understood, but currently at NBRO, we are trying to clean those drains and get them back to the initial capacity, but they are working, but along with some sort of little blockage. So there were some pumping wells here, right? When sometimes during the periods of heavy rainfall, they use these pumping wells to lower the groundwater table further, right? So the railway track, how it is seen now. Right, so that's one of the most famous landslides in Sri Lanka, where we have successfully stabilized by subsurface drainage along with surface drainage. So still today, the railway is operating without any disruption. Then I'll come to the Badulu Sirigama landslide, which was again rectified by subsurface drains. Earlier, I showed you the instrumentation done at this particular landslide. So it was rectified in 2016. See, with a series of long subsurface drain network arranged in a fan-like pattern at 6 different levels. In these fan-type drains, these individual drains were of length like 40 to 60 meters, right? Because to cover up the necessary area, you need that. So that shows the area of the landslide. It is closer to the Overvillasa University of Sri Lanka. I have shown this picture to you in the part 2 presentation, right? The landslide boundary and the instrumentation. So these were accurately established through topographic surveys, cross-sectional surveys, and mapping done with drones, unmanned aerial vehicles, and also 5 boreholes were done to establish the subsurface condition, along with seismic surveys and the resistivity survey. So a very detailed investigation, surface and subsurface, was done at this particular site to identify the landslide sort of slip surfaces and the subsoil profile. So with the investigations, it was found there is a thin colluvial layer at the top, and underneath the residual soil and moderately weathered rock. So these are the established shear strength characteristics. With the surface features and the subsurface and the results of the subsurface investigation, it was found that there are three distinct failure surfaces. It was not the failure, it is failure is happening along this boundary, colluvial residual soil boundary, and it is made up of three different failure surfaces named lower slide, middle slide, and upper slide, right? So the three different slides are happening in here under these topographic and subsoil conditions. So the groundwater table is rising during the rainy season. So the landslide is moving slowly during the periods of heavy weather, heavy rainfall. Now, there were a number of houses here that were severely damaged, right? So the road is further down here. So we need to rectify that, right? Because this is an area where a lot of people were living. So with detailed analysis, the method of rectification was established. So surface drains were proposed. The blue lines were the surface drains, right? And then these fan-like things are the plan orientation of subsurface drains. So it is going down, right? So that is the landslide is the downward slope. So at different levels in the slope, right, we had these fan drains. So that is the width of the landslide, right? It is necessary to cover that width to sort of allow rapid dissipation of the pore pressure in that width. So these fan type things, as I mentioned before, these are 40-60 meter long fan drains, right? There were 6 lines of fan drains from top to bottom, and you can see that here as well, right? Installed to facilitate the subsurface drainage and enhance the stability of the slope, preventing failure during the periods of heavy rain. Right, each fan contains 8 to 9 individual drains. So this is the way to install this subsurface drainage measures with minimum disturbance in the most effective manner. Some pictures of surface drains and subsurface drains. At one location, right, there were drilling in these radial directions. So the water collected from the subsurface drains were taken to one manhole, and then this was sent down the slope through another drain. Now this process was numerically simulated later with a detailed research, right? We did a 2-dimensional analysis, modeling the infiltration and the subsurface drains with SeepW software, and SlopeW software was used to analyze the stability. Also, we did another analysis with Plaxis 3D software, right? So in the 2D analysis, we modeled the identified failure surfaces, right? So stability was evaluated on the identified failure surface after the infiltration analysis. But in the 3D case, we didn't finite element. It was a finite element analysis through Plaxis. No assumptions were made regarding the failure surface, and the critical failure surface was obtained using the C5 reduction technique available in the software. So for the details of that, two-dimensional plane strain analysis with limit equilibrium approach. Most critical cross-section was identified with the site investigation data. Slip surfaces were fully specified as they were identified. And factor of safety with respect to slip surface subject to different conditions were determined using the Spencer method, because this is an uncircular failure surface. Then in the finite element analysis done with the Praxis, a real scale 3D model was developed, and different irregularities, different soil layers were incorporated in that. Factor of safety defined using the strength reduction approach available in that. So coming to the details of the 2D analysis. So this is the idealization of the fan type drains in plane strain, right, at 6 different levels, and the level A at the bottom top, A, B, C, D, E, F. There were 6 fan drains. Topmost one is A, drain A, D, B, drain B, drain C, like that. We analyzed the simulating the process. We analyzed the effect of the construction sequence on achieving the stability, enhancing the factor of safety. That is basically with what is best to do. What are the changes happening if we do a top-down installation? Now in this slope, there were no geometry modifications required. Within the existing geometry, these drains were installed. So we could have done it from top down or bottom up. In certain situations where geometric changes are necessary, there is further restraints. But here we could have done it from top down or bottom up. So in the case 1, say we assume that everything is installed simultaneously, but that is not practical. When we install top-down installation, first the drain A, then A and B, then A, B, C, A, B, C, D, E, like that. Case 3, bottom up. So we install the bottom one first, DF, then F and E, right? F, E, D, right? So we assume there will be 3 days time gap between the installation of the drains at different levels and mold it. So these are the results for the top-down installation. So if you remember, we had 3 different slides, upper one, lower one, and the middle one. With the top-down installation, right? So only the A, drain B, drain C installed at this particular date. So the factor of safety of the upper failure surface, upper slide, improved rapidly, improved fast, and then came to this value. And the middle one started to improve only after installation of drain C. The lower one started to improve only after the installation of drain F, right? The upper installation of the upper drains did not have much impact on the stability of the lower slide. So then, now this shows the bottom of construction sequence. So the bottom drains were installed first. So you see that the factor of safety of the lower slide improved fast, right? In the upper one, the factor of safety did not improve until the installation of the drain B at the second level in here, right? So here we see a clear indication of how the factors of safety will develop in different regions of the slope with the construction sequence. Now, then we did a study to see how the rectified slope would respond to a critical rainfall. from the past rainfall records, we generated this critical rainfall in the site, right? And now we modeled the presence of this system of drains. So if these drains are there during the this rainfall event, right, with this very heavy rainfall, there will be a reduction factor of safety, but it will be greater than 1, right? And with the cessation of the rain, factor of safety will be regained. So that is for the upper slide, and this is the lower slide. So there, the factor of safety reduction is much lower, and the middle side behavior is there, right? So once we install a rectification measure, we can see how the slope would respond to a critical rainfall that could occur thereafter. We did the analysis with the composite failure surface as well, right? Combining the three, we get the composite failure surface and model the installation of drains from top-down case, the bottom up. So we found that after installation of all 6 level drains, so it ends up with the same safety factor. So this shows how the pore pressures will, initial pore pressure, how that would drop down with the installation of the drains at different levels. So this research study was done as a master's research, making use of the data available from the project. Now, in the project, we did this implementation of the subsurface drainage measures, but these analyses were done subsequently with that data, right? This is the stability of the composite failure surface. Previous slide shows the stability of the 3 individual identified failure surfaces. So with the composite failure surface, how it would respond to this critical rainfall event. So during the event of this rainfall, right? So there is a lowering of the factor of safety, but with the cessation of the rainfall, it is regained, right? So the detailed aspects are given in here. During the drain out, initial high ground table conditions, some residual flow channels are already established. So this light infiltration during this period is easily drained through these residual flow channels. When large infiltration occurs, the capacity of residual flow channels are exceeded, therefore water accumulates in soil body, and that causes this reduction of factor of safety. Right. So that completes this part 3 presentation, which is on rectification of slopes through surface and subsurface drainage. Next one, in the next part, we will talk about the combined effect of drainage and structural solution. Thank you.